The citric acid cycle is the final stage of the breakdown of carbohydrates, fats, and amino acids released from dietary proteins. Acetyl coenzyme A and oxaloacetate feed the citric acid cycle. The acetyl group gets oxidized to two molecules of carbon dioxide, and the high-energy electrons from the oxidation are transferred to NAD+ and FAD. We'll now take a look at the fate of the acetyl group of an acetyl coenzyme A as it passes through all of the steps of the citric acid cycle. This slide shows an overview of the citric acid cycle, or the Krebs cycle, and we can see that acetyl coenzyme A enters the citric acid cycle here. Then we proceed through all of these intermediates, which are highlighted in yellow. So we go from acetyl coenzyme A to citrate to isocitrate, so on and so forth. And there's a mnemonic that I like to use to help me memorize all of the intermediates, which are highlighted in yellow, and that mnemonic is: citrate is Krebs' special substrate for making oxaloacetate. So citrate starts with the letter C, then isocitrate, then we have alpha ketoglutarate, then succinyl coenzyme A, then succinate, fumarate, malate, and oxaloacetate. Again, it's citrate is Krebs' special substrate for making oxaloacetate. Reaction 1. This is a condensation reaction between the acetyl group of acetyl coenzyme A and oxaloacetate. It is catalyzed by the enzyme citrate synthase. The product formed is citrate, a 6-carbon molecule with 3 carboxylate anions. And since the conjugate acid of a carboxylate is a carboxylic acid, this is where the name the tricarboxylic acid cycle comes from. In reaction 2, the enzyme aconitase catalyzes the dehydration of citrate, producing cis-aconitate. The same enzyme aconitase then catalyzes addition of a water molecule to the cis-aconitate, converting it to isocitrate. The net effect of these two steps is the isomerization of citrate to isocitrate. Reaction 3 is the first oxidative step of the citric acid cycle and is catalyzed by isocitrate dehydrogenase. It is a complex reaction in which three things happen. The hydroxyl group of isocitrate is oxidized to a ketone, carbon dioxide is released, and NAD+ is reduced to NADH. This is an oxidative decarboxylation reaction, and the product is alpha ketoglutarate. And of course, you can see that isocitrate is being oxidized because we're losing hydrogen atoms, and NAD+ is being reduced to NADH by the gain of a hydride. In reaction 4, coenzyme A enters the picture again as the alpha ketoglutarate dehydrogenase complex carries out a complex series of reactions similar to those catalyzed by pyruvate dehydrogenase complex. The same coenzymes are required, and once again, three chemical events occur. Alpha ketoglutarate loses a carboxylate group as carbon dioxide. It is oxidized and NAD+ is reduced to NADH, and coenzyme A combines with the product succinate to form succinyl coenzyme A. The bond formed between succinate and coenzyme A is a high-energy thioester bond. In reaction 5, succinyl coenzyme A is converted to succinate. Succinyl coenzyme A is converted to succinate in this step, which once more is chemically very involved. The enzyme succinyl coenzyme A synthase catalyzes a coupled reaction in which the high-energy thioester bond of succinyl coenzyme A is hydrolyzed and an inorganic phosphate group is added to GDP to make GTP. A second enzyme, dinucleotide diphosphokinase, then catalyzes the transfer of the phosphoryl group from GTP to ADP to make ATP. In reaction 6, succinate dehydrogenase then catalyzes the oxidation of succinate to fumarate in this step. The oxidizing agent flavin adenine dinucleotide, or FAD, is reduced in this step. Something you always have to keep in mind is that if you have oxidation, reduction must be occurring as well. The succinate is being oxidized by the loss of 2 hydrogen atoms to produce fumarate. Those 2 hydrogens are used to reduce FAD to FADH2. In reaction 7, addition of water to the double bond of fumarate gives malate. The enzyme fumarase catalyzes this reaction. This reaction is a biological example of the hydration of an alkene to produce an alcohol. In the final step of the citric acid cycle, malate dehydrogenase catalyzes the reduction of NAD+ to NADH and the oxidation of malate to oxaloacetate. Because the citric acid cycle began with the addition of an acetyl group to oxaloacetate, we have come full circle. This reaction is a biochemical example of the oxidation of a secondary alcohol to a ketone. So my secondary alcohol gets oxidized to a ketone, and NAD+ is reduced to NADH.